So, good evening. I'm Nadir Murru, and I'm Associate Professor of Algebra at the Department of Mathematics of the University of Trento. So, in this lecture, we will see the NTRU crypto system. The acronym NTRU stands for nth degree truncated. And indeed, this crypto system is essentially mainly based on the use of polynomial rings quotiented by an ideal generated by a polynomial of degree n. And so this is the reason for this acronym. These crypto systems belongs to the family of post-quantum crypto systems and belongs to the family of lattice-based ones. Its first version is due to Hofstein, Pfeiffer, and Silverman, and it was published in the 90s. So in this lecture, first of all, we will see this classic version. So the first version of this crypto system. And we will introduce the notation, the framework, and the core idea of the scheme that is very important for seeing in the final part of the lecture, for seeing one of the main improvement of the NTRU scheme. Indeed, this first version that is very nice and very important from a didactic and not only point of view, is also very important for understanding the core idea of the crypto system and then for trying to improve it. Indeed, the first version had some flaws and some problems regarding the implementations and required some changes for the next competition. Indeed, the submission for the next competition of the NTRU scheme was different from this classical version that we see in the first part of the lecture. And then, in particular, at the end of the lecture, we see the version named NTRU HRSS. That is a version also suitable for obtaining a key encapsulation mechanism. And one of the finalist scheme of the next competition is called again NTRU, like the classical scheme that we see, but it is just emerged.
Excuse me.
Yes.
May I ask, because I see the first slide.
Yes.
Is it normal?
Yes.
Okay, thank you very much. I'm sorry.
I'm just doing an introduction.
Okay, thank you very much. I'm sorry.
Then you will see the next slide.
Thank you.
You're welcome. And I was saying that the finalist scheme for the next competition is called just NTRU, like the first version of that we will see in this first part of the lecture. But this version in the next competition is just emerge of the NTRU encrypt scheme that we don't see in this lesson, which is and this is just another modification of the classical NTRU scheme, merged with the NTRU HRSS chem scheme that we will see in the second part of the lecture. Okay, so we can start with our lesson. For presenting NTRU, we start fixing some notation and some parameters involved in the scheme. In the following, we will always use the letter NPQ that represent some integers. N is always a prime number. PQ are not necessarily prime numbers. The only condition that we require about these integers is that their greatest common divisor is equals to 1. and usually Q is taken greater than P. When we will see the implementation, we will see that the number P is almost always taken equals to 3, just 3, and Q is very often a large power of 2. Okay. Then we have this important ring that we call R, and it is the ring obtained quotienting the ring of polynomial with coefficients in Z by this ideal. This is very important. Indeed, all the calculations that we will perform later are performed in this ring. So when we perform some operation, some multiplication between polynomials, we always work in this ring. So remember that we work modulo this polynomial x to the n minus 1. It is very handy to use. Then we have to define also other sets of polynomials. And in particular, we need 4 sets. These LM, LF, LG, and LP. LM is defined in this way, is the set of polynomials with a degree at most n minus 1, and whose coefficients are in this interval. And this is essentially, as we will see later, the space of the plain text. Then we have also these 3 sets of polynomials, where are we call these ternary polynomials, since the coefficients of these polynomials are just minus 1, 0, and 1. And we require for the polynomials chosen in this set that the number of ones is equals to this integer, to this fixed integer df, and the number of coefficients equals to minus 1 is equal to df minus 1, and the remaining coefficients are 0. And similar the definition of these other sets. Okay, so we are ready for seeing the NTRU scheme. As usual in public key crypto systems, we have to define 3 phases: the key generation, the encryption procedure, and the decryption procedure. So regarding the key generation, we start in this way. We start with sampling 2 random polynomials, f and g, in these sets. So where we require some conditions about the coefficients. And we have to choose these polynomials such that the polynomial f is invertible in our ring R, of course, and also after the reduction of the coefficients modulo p and modulo q. So thanks to the extended Euclidean algorithm, one can evaluate the inverse of f modulo p and modulo q, and we name this inverse fp and fq. After this evaluation, we are ready for concluding the key generation phase, evaluating the public key. The public key is just obtained from the polynomial g that we have sampled in this set, multiplied by the inverse of f modulo q. Remember that all the calculations are performed also in our ring R. So we have that in this scheme, the public key is this polynomial h, and the private key is composed by these 2 polynomials, f and the inverse of f modulo p. We don't need fq and g for performing the decryption of a ciphertext. So the private key is just composed by these 2 polynomials. Of course, you have to maintain secret also the polynomial g and the polynomial fq, but they are not important in the phase of the decryption. Okay, so let's see the encryption procedure. First of all, let's note that this set LM that we introduced before is the set of the plain text. And we take plain text in this set. For encrypting this polynomial, this plain text, we have to choose a random polynomial phi in this other set. And so one can evaluate the ciphertext exploiting the public key age. So the ciphertext is just obtained multiplying the public key age by the polynomial phi that you have randomly sampled in this set and multiply by the integer p. Then you sum with the plain text. All the computations are performed in R, and also we have the reduction of the coefficients modulo Q. Note that just knowing the ciphertext C and the public key age, it is not possible to recovering the plain text M. And so this is a safe procedure for encrypting our plain text. The decryption procedure is also very simple. And in particular, first of all, you have to evaluate, sorry, this is C and not E. You take the ciphertext C and you multiply for decrypting. So the decryption procedure is performed only by one that, that has the private key. For decrypting a ciphertext C, you multiply it by the first part of the private key, it has the polynomial f, and reduce modulo Q. You get a polynomial A. This polynomial, and this is very important in NTRU, is a polynomial whose coefficients must be in this interval. Otherwise, the decryption can fail. But we will see that this polynomial A has almost always the coefficients in this range. And moreover, in the HRSS version, this is guaranteed by the selection of the parameters, essentially. So the last operation for recovering the plain text is this one. After that you have obtained the polynomial A, you multiply it by the other part of the private key. It has the polynomial fp and reduce all modulo p. Okay, so let's see the proof of correctness. So let's see why the decryption procedure works and why sometimes we can have some problems. Some failures can occur during the decryption procedure. And then in the next slides, we will see how to avoid this problem. And so on. We will see also why this problem, we don't have this problem in the HRSS version. So when we evaluate the polynomial A, actually you are evaluating this polynomial and you are reducing it modulo Q. If you remember, the public key age is this one. So it is related to the inverse of the private key modulo Q. So this is the important issue. Indeed, in this way, these two polynomials becomes just one, and you are obtaining just this polynomial. So the polynomial A corresponds to this polynomial. The polynomial A has almost always all the coefficients in this range. If we have this, this means that in this case, the polynomial A coincides with this polynomial P, phi times G and so on in R, because it has not been reduced modulo Q. And so it is equals to this polynomial in R. So then we need this reduction. Then we perform this this multiplication between A and Fp, and reducing modulo P, we delete this part from the polynomial A, and exploiting Fp, we remove also the polynomial F, and we just obtain the plain text M. And we have recovered the plain text in this way. Okay, so we have seen the NTRU scheme. Now let's see some details about the parameters. Here we introduce a norm for the polynomials in R. These norms are important in this proposition that we just see the statement. It is important, this proposition, because it gives this relation between the norm at infinity of the product of these two polynomials and this squared norm. And in particular, we have this bound for the product of this polynomial with respect to the norm at infinity. In this way, we can exploit the previous proposition and these norms for avoiding failures in the decryption procedure. Indeed, essentially, for avoiding failures, we just need that this condition is satisfied. Indeed, if this condition is satisfied, essentially we have that our polynomial A has coefficients in our desired interval. And one can obtain some conditions on the private key and on the plain text in order to guarantee this condition. And so we can take a plain text, or we can take a private key in order that it is almost always guaranteed that the polynomial A has coefficients in our desired interval. Okay, so here I skip this slide, but you can see this in details when I will give you this slide. These are just the parameters selected for having moderate security, high security, and the highest security level in the classical NTRU scheme. You can note that, as I have said, the integer p is always chosen equals to 3.
Sorry, I have just one question for this slide.
Yes.
Can I ask you?
Yes.
Okay. How do you estimate moderate, high, and highest? So
okay.
What's the definition of security actually?
Okay, this is related with the next slides, and essentially it is related to the possibility to perform a meet-in-the-middle attacks that and a little improvement about the brute force attack. So if you take these parameters, for instance, the key security is given by 2 to the 50 with respect to this attack meet in the middle. And essentially this attack meet in the middle is just a brute force attack. Indeed, an attacker can recover, for instance, the private key by trying all possible polynomials in the set where the private key is chosen. Or similarly, also for the polynomial G. If you obtain one of these two polynomials, you can recover the private key. Similarly, you can also recover the message by trying all the possible polynomial phi. Indeed, if you remember, this polynomial is used for in the encryption phase, in the encryption procedure. And this brute force attack can be improved by trying to split the private key that you don't know into polynomials and try to find these polynomials f1 and f2 in some way. In this way, essentially, you can improve a little this attack. And in this case, the key security and the message security are equals to these values that are exactly these levels that I have shown in this slide. Okay. We can see also the reason because the classical NTRU scheme is a scheme belonging to the family of lattice-based schemes. Indeed, one attack can be performed exploiting the theory of lattice. Indeed, it is possible to show that you can construct, starting from the public parameters, starting from the public key, these are the coefficients of the public key, you can construct this matrix where this alpha is a value chosen in a convenient way. So you can construct this matrix, and if you construct this matrix, you can take these rows, the rows of this matrix for generating a lattice, and the lattice that you have generated contains this vector where there is the concatenation between the private key and the polynomial g, the first part of the private key. And so if you choose in a good way this parameter alpha, this vector is the shortest vector of the lattice generated by the rows of this matrix. And so you can reduce the problem of attacking NTRU to a problem of finding a shortest vector in a lattice. Okay, I skipped just this slide, and we can start with the HRSS version of the NTRU scheme. So this version is very similar to the classical version, but there are some differences and some improvements. In particular, we have also some recommended value for the prime n. It is chosen equals to 701. And this is also the recommended value for the parameter q. Then, also in the HRSS scheme, we have the ring R where all the calculations are performed. But in this case, sometimes we also exploit this polynomial for obtaining this ring. And so sometimes we perform some calculation reducing also modulo this polynomial. And so we have the ring RQ, that is essentially the ring R where we reduce the coefficients of the polynomial modulo Q. And this SQ is the ring obtained modulo this polynomial and reducing then the coefficients modulo Q. Also in the HRSS version, we have the sets S2 and S3 that are exploited in some calculations. So we can see the three phases of the HRSS version. The key generation phase is a little bit different from the classical one. In this case, we just randomly choose a polynomial f in this set S3. It is given, it is obtained in this way. So quotiented by Tn. Sorry, these are all capital letter. And then you compute the inverse of f in S3 modulo also p. Then you have to choose the public key age, and you can sample it using the set RQ defined in this way, such that these conditions are satisfied. In the NIST submission, you can find some algorithms that allow to sample the public key age so that these conditions are satisfied. So also in this case, we have a public key named age that is this polynomial, and we have a private key that is obtained that is given by these two polynomials. For the encryption procedure, we can take a plain text M as a polynomial in the ring R. And for encrypting it, you randomly sample a polynomial R here, and the ciphertext is just given in this way. So you multiply the public key by R, and you sum the plaintext M. All these calculations performed in the ring R and modulo Q. So the decryption procedure is very similar to the classical decryption that we have seen for NTRU, and indeed we don't see the proof of correctness. You can derive, you can obtain the proof of correctness of the decryption procedure following essentially the same steps that we have seen before. So you take the ciphertext C and you multiply it by the first part of the private key, and you get a polynomial A. Then, after that you have obtained the polynomial A, the plaintext is recovered performing this multiplication in this set. And so this is essentially the IJAR-SS version. Starting from the NTRU IJAR-SS encryption scheme, you can also derive the key encapsulation mechanism. And in the encapsulation procedure, you just have to use an hash function. Usually it is shake 128. And you use this hash function for constructing the shared key. And then you have to choose an element M in S3. So this element is sent encrypted using the previous scheme to the receiver. And the decapsulation procedure for recovering the shared key is obtained by the usual decryption. Okay. In this version of NTRU, as I have said, there are also some algorithms for performing both the encoding and the sampling of polynomials. The encoding, I mean the encoding of for passing from polynomials to strings of bits and vice versa, since in the NTRU scheme we always work with polynomials, but usually plain text, ciphertext are strings of bits. So you need some encoding algorithms. This is the version provided in the IJAR-SS version. Moreover, you also need some sampling algorithms for randomly sampling the required polynomials, the necessary polynomials that are used in the scheme. For instance, this is the sampling algorithm for generating a random polynomial in the set S3. And similarly, you also have many other sampling algorithms for generating, for instance, the public key age that is very important. Okay, so we have almost finished. We are almost on time. We can see some advantages and disadvantages between the standard classical NTRU scheme and the version that we have seen, the IGRSS version. In this final version that we have seen, we have this important feature. We don't have decryption failures. This is essentially thanks to the parameters selection and also thanks to the phase of key generation in the properties required for the public key. Also thanks to some conditions that we have on the plaintext. Moreover, we don't need padding mechanism for obtaining semantic security. And the secret keys are always invertible thanks to the sampling algorithms. These are the two disadvantages that we have, and in particular in the IGRSS version, we have to work with larger moduli, and also we need to evaluate more inverse modulo P, more than the classical version. Okay, so I have finished with this presentation. So